All right, let's go ahead and get started with lecture 5, going more in depth to simple linear regression. So we'll start by recapping a little bit from last lecture. Then we'll dive a bit into what exactly a correlation is, how it's calculated, and some intuitive ways to think about it. And I'll try and build up some of the intuition that you can get for correlation. This type of intuition will be especially useful for further machine learning knowledge, especially when you have to think about correlation matrices and all different types of stuff like that. Then we'll talk a little bit about how linear regression can be thought of and compared to other types of related models that we've looked at, and then we'll talk a little bit about linear algebra and why we need linear algebra when we move beyond simple linear regression models and move into more complex linear regression models, namely those type of regression models that involve multiple parameters beyond just the basic one intercept and slope. So that's get through in this lecture. And remember, you can always ask questions online, and we'll have a few questions that I'll ask you in this lecture, and then you just pause the lecture and try to answer them, or work with somebody that you're studying with to try and answer them, and then continue the recording, and we'll go through the answer. Okay, so let's start by recapping simple linear regression. So in last lecture, our main goal was to try and take this data right here, which is, we have our independent variables like home departure time and our dependent variable minutes. And we want to know, given some time when you left, either 6, 7, 8, 8:30, whatever it is, what would be the predicted minutes that it takes to get from home to work. And in order to do that, we try to fit the best line. Now, of course, we could create any line, and any of these lines could be, viable. But there is one best line when minimizing for mean squared error, which is what we were doing. So that's a typical differentiable loss function to use for linear regression like this. And when we did that, we found that we got some line. We'll go with purple. We found that we had some line, probably something like, like this. And we have our intercepts, in that case, sometimes something around 115 or 118 or something, and this is our slope. And so this was the best line that we found for this specific data set. And then we can use this line now to make any prediction based on any time that we left. So this is what we've done so far, and this is a really big departure away from what we originally did when we had just the constant model. We were regardless of whatever our departure time was, we always predicted one value. So if the constant model was 90, then whether we left at 6 or 7 or 8 or 8:30, we'd always predict 90. And so now we have a line where we can go here and over here and say if we left at 8 a.m., it should take about 80 or so minutes to get to work. So this is the progression that we've made. And to do that, we've used this idea of the modeling recipe. And the modeling recipe is a nice way to think about this because it breaks down these ideas of choosing some sort of model, and then you have to fit a loss function to that model and minimize it, which is by and large how pretty much all machine learning really kind of works. So in this case, we had, we'll stick with purple. We had our hypothesis function, and for the case of linear regression, we had W naught and that's plus W sub 1 times x. And remember that W naught was our slope, and W1 or W sub 1 was our W naught was our intercepts, and W sub 1 was our slope. Okay, and so in this model, our hypothesis function, we're trying to determine what the best intercept and slope would be. Those are our two parameters. And the loss function that we chose was least squared, and that was y sub I, hypothesis function x sub I, and that equals y sub I minus h x sub I squared. And if you remember, this hypothesis function of x sub I is really just kind of a fancy way, that would be this right here, is just a fancy way of saying we have an actual value minus a predicted value squared. And make it a little better. Okay. And our goal is to kind of pick the slope and y-intercept that makes that loss function as small as possible. So in order to do that, we'd start with one over n, and this is just the sum for y sub I minus h x sub I squared. Okay, and now remember, we want to take this thing and we want to determine what the best parameters are in here for this hypothesis function. And we already know what that is. We have that up here. So we can really just take this a little bit further and say that the squared for W naught and W1 is equal to this. And we can actually replace this x sub I in here with what we know what we're looking for. Actually, we do replace this too. And that's going to be y sub I minus W naught plus W x sub I squared. Right? So we've gotten this right here. And this is what's going to allow us to determine the best slope and y-intercept to minimize our loss function as much as possible. Okay, so, and how do we do that? Well, again, last lecture we found these equations right here, which does that for us. So, yeah, you can, as we said before in this slide right here, we can draw any number of lines that we want, but the best line, which was this that we found, the best line is determined by minimizing mean squared error. In order to minimize mean squared error, you need to use these two equations. for this is our W sub 1 star and our W naught star. And this is, equations that we proved and found from last lecture. And these are the ones that yield us our optimal parameters. And those optimal parameters give us the regression line. And again, this is the regression line. So I'll put that. Okay, so because regression lines are happy because they're the minimum and best line for that data set. So this is what we use to get that optimal regression line. And, this is pretty cool. We have here our, just to maybe reiterate this, the best intercept, which is our W star naught. And then the best slope, which is our star. So yeah, that's the best slope. And how these things are determined, just like if you think back to a few lectures ago where we had this concept of this number line, and on there we had like screen, we had a data point here and here and here and here, and we found that somewhere over here was a mean squared error, which minimized the distance, the Euclidean distance between this point and these 3 points, so that when you sum them all up, the Euclidean distance on the left-hand side was equal to the Euclidean distance on the right-hand side, summed for all these different points. And the same concept applies for here too. We have this regression line here, and this regression line is constructed from this 142.25 and this minus 8.19 right here, and this is our optimal slope. This is our optimal intercept, and those two things combined gives us this regression line right here. And this regression line is acting just like this number line example, where we have these data points, and these data points all have errors in them. And these errors are the distance away from a line. And when you sum up all these distances on both sides of the line, and when all the data points are minimized such that if this line was to move anywhere else, it would increase the sum of these distances. This is why this is the regression line, because these distances here, when summed up between all these data points, are minimized. And so that's just another way of saying that there's no other line for this data set that has, so maybe I'll write this out. So let's do it over here. So no other line exists for this data set that will yield a smaller average squared error. And this is kind of the power of linear regression. So you know, now that we've found this regression line, we want to really start to begin to understand how do we interpret this regression line in the context of like the data set and the model that we're building. And this is an important thing to do because later on in your machine learning careers, when you begin to look more at like L1 and L2 normalization, and whether you want to do things like using regression models that are more specific, like lasso and ridge regression or elastic net regression, which penalizes your data set for different types of issues like outliers. If you have a firm understanding of kind of the theoretical underpinnings of the regression model, then making better choices when you're doing linear regression modeling becomes a lot easier. And don't fall into this trap of just thinking like, just use neural networks or some really fancy sophisticated algorithm. In real world problems, really the easiest algorithm you can get away with, which may not always be the most accurate or whatever your end result is, precision or recall. Simplicity, interpretability, right? Like this is a simple model. It is 100% interpretable. These things are really important in the real world. And if you can solve a real world problem with an interpretable and simple model, it's pretty much almost always better than something more complex and that's difficult to maintain in the real world. So there is always a space for linear regression, and more commonly referred to the general linear models. So logistic regression, linear regressions, all these types of basic linear models, they really do a lot of wonders. So this stuff is important to learn and understand, specifically understanding its connections to other models, other related, unrelated models. So and in order to make this really useful at all, you're always going to be doing regression pretty much with multiple variables. So this very simple examples that we've been going through using one slope and an intercept for the one variable that we're using, in this case, home departure time. This will get more complicated, but it's pretty much going to be the same thing we've been doing. It's just we're going to have to make use of like linear algebra to resolve the extra dimensions, and we're fitting a hyperplane instead of a line here. And we'll get more into that stuff a little bit later. But just to keep things kind of light and interesting at the moment, why don't we go ahead and try and work on this problem. And when you're looking at this problem, I want you to really pay attention to what the question's asking you and think about it from the kind of like mathematical background you have. I'll give you a hint. There's a hard way to answer this problem, and there's an easy way to answer this problem. And the easy way is entirely dependent upon reading the question and really understanding what the question's asking you. So you can go ahead and pause the video now, and then we'll pick it back up and look to answer it. Okay, so as good UCSC test takers, we probably already know that this is not going to be the answer. Not because you just know that, but when you got the 3 5s like that, and this is a 10, it's probably not going to be this one. But we'll go ahead and see why. Really, the most important thing to think about is this idea: 2 points, right? So when we consider this data set with just 2 points, and we want to fit a linear hypothesis function to this data set using squared loss. So essentially, we're doing this, but instead of having all these points, right, we're only going to have like 2 points. So maybe our data set is just this guy over here and like this one right here, and that's it. So when we consider data set with just 2 points, we want to fit a linear hypothesis function to this data set using squared loss. what are the values of W naught star and W sub 1 star that minimize the empirical risk? So what are the best intercept and slope? And what you can do is you can take this data set, since it's small, and you can run it through these equations here. And that will yield you the best W naught and W1 star, because we've shown and proved this, and we know that it will give us our best intercept and our best slope. However, these equations are somewhat nasty, ish, but we can do something better, because since we read the question carefully, which you always want to read the question carefully, especially in a class like this, we know we have just 2 points. So we can just plot the 2 points and get the slope itself. And then we have an equation for the intercept that we can use. So what would that look like? Well, let's go to blue, and let's start with black maybe, and create a plot. All right, and let's put down 2 points now. So it's 1, 2, 5, somewhere around. Let's make it a little smaller. So we'll call it 2, 5, somewhere around here. And then 4 and 15 would be around here. Okay, so we want to fit a linear hypothesis function that minimizes the empirical risk through squared loss. So we know that we want to draw a line, and a line that goes, we can draw any line, right? If we want to draw the line that minimizes that distance. So what's the best way to do that? Well, we just draw a line that goes through, that goes through these 2 data points. That's what we want to do. Because if it goes through both data points, then we know the minimization will be 0, because there's no distance. And a line segment can go through 2 data points. So we want this line right here. And it's not really drawn too well, because the y-intercept, the intercept is not, the y-intercept is not negative. So just so that this doesn't look weird, let me redraw the 4 and 15. So it'll be sort of like this. Really trying to keep it above the origin. Okay. Yeah, we can do better. All right. Anyways, probably like, come on, get on with it already. Just draw the line. We get it. All right. So if we're going to go ahead and solve this, we're going to do, let's get the slope first. So that's y sub 1 star, which we know is our slope. That's just equal to these 2 lines. That would be what? We have our 2 points, 2, 5, 4, and 15. So it would be 15 minus 5 over 4 minus 2, which gives us 10 over 2, which gives us 5. So this is what we're going to use for slope, and we know that this can't be 10 anymore, because we have 5 as our answer for W sub 1 star. And so then now that we have that, we can go ahead and use it for intercept, which will be 4 times 5 plus W naught So 4 times 5 plus W naught star, which is equal to 15. And then we can just use a little bit of algebra and simplify this to W naught star equals 15 minus 20, which equals -5. And make this our answer. And that's just simple algebra and the equation for a slope between 2 points. So we don't actually need to use these fancy equations, though if you did want to, and you can try it out, you'll get the same answers. However, like for example, if this is a test question, you would save yourself a lot of time by just realizing it's 2 points. Even if you were to just draw this out and explain, and you didn't really know how to remember how to do this because it had been a long time, yeah, that would still yield you a good amount of points, because from our point of view, this is just algebra and math. But this is like the conceptual understanding of knowing what you could do or need to do versus the mechanical, like the mechanical approach to just solving a problem, which is with computers nowadays is not as important as being able to get the conceptual stuff down. Granted, this is still important, but this is the more important part of it. Okay, so hopefully that question gave you something to think about. Remove this thing. We'll go ahead and talk a little bit about correlation next. And another interesting thing with correlation that we'll also get to see is that we will be able to express the regression equations for finding the optimal slope and intercept, so W naught star and W sub 1 star, in terms of correlation. So this will be a nice deep dive into correlation. You'll be able to see how they all kind of relate together now. Okay, so we have this idea of the correlation coefficient, and you've seen this before, for example, in like DSC10. And this is I suppose a good thing to think about first is this idea of association versus correlation. And so association can be any pattern that you see in a data set. So if we have here, like, for example, this plot versus this plot. In this plot, there's a clear linear association within the data, as well as a correlation. And correlation is always linear. In this plot here, we do have an association because there is a very strong pattern. However, this pattern seems to be something that's more of like a quadratic pattern and not a linear pattern. So while this plot here has strong association, it would have extremely weak correlation. And so just to make that explicit, where should we write this? And at the top, we'll put a so again, correlation, linear pattern, and a linear pattern we say is essentially resembles a line, and so this is a linear pattern or linear association, whereas association equals any pattern. So I suppose you could say association is like a superset, which includes correlation. Correlation is just one type of association. So let's go through and probably should have written these in different colors, but that's okay. Yeah, let's go ahead and do that just to make this a little bit easier. So in this case, for this first plot, in the top left here, we would say that this has really no association, neither correlation or any other type of association. So this is just no association. And if it's got no association, then it definitely has no correlation. Right, because for this plot, I mean, when we do run the correlation coefficient on this, we're going to get something that kind of looks like that, but it's going to be extremely weak, and we'll see why. Okay, so this next one down here, this has strong association, but no correlation. This top right one here has a strong association. And what type of association has strong positive correlation? Oh, garbage. Correlation. And the reason why it's a strong positive correlation, well, one is because positive correlation, it's got kind of an upwards rather than a downwards trajectory. But we say it's strong because we say correlation is strong, like absolutely perfect correlation. Remember, correlation is from -1 to 1. If you've got a correlation of 1, you would essentially have just a line of dots. They'd all fit on one line. And so as your data points move further away from the line, right, you can think of it as kind of like a tube, and right, so this is like the tube. As the diameter of the tube gets larger, right, then the amount of correlation goes down. So I can put a tube around these data points, and it would be a much smaller tube than what would be needed to go through these data points. And because of that, this top right one has stronger positive correlation than this bottom right one. Where this still has, we could say a, moderately strong association. I'm going to say moderate association. Keep it easy. We'd also say that this has a moderate positive correlation because it's still, going upwards like that. Correlation and specifically in, that'll be the next slide we talk about the correlation coefficient, but correlation as it ranges between -1 and 1, maybe we'll use blue for this. If the value is negative, then the line will be going downwards. So means the line kind of goes like that, which should be like a value between like -1 to 0. The positive correlation like that between 0 and 1. And of course, like, the correlation for this one is probably going to be like 0.02, something. Whereas the correlation for this is probably going to be like, 0.80 or something. it was actually when I taught Cogs 9, there was a really a student brought up a game where it gives you a plot like this, and you have to guess what the correlation is, and the further away you are, the more points you lose and it's kind of like a speed game until it goes down to 0. I think that student got like 60 plots in a row before he ran out of points. And I think I got up to like 45 or something. He was quite happy with himself. So there you go. You can get really good at that. I don't know if it's a functionally useful skill, but I suppose bragging rights are always fun to have. It's not that positive or negative correlation is, it's not like one is better than the other. They're both perfectly valid. It's the closer you get to -1 or 1, the better your correlation is, which means there's a stronger pattern. And as your correlation gets closer to 0, you have no pattern, certainly no linear pattern. So that's kind of how the ranges work. So regardless of whether these points are going this way or if they were all, kind of going like that, that it would be a negative at that point, then this is all fine. But this right here, not good. There's nothing there for us. There's just, nothing going on. This, though, no correlation at all, but there's a very strong pattern here, and we can uncover it using other means to try and understand it. Okay, so the correlation coefficient that we're using, and this is typically, there's lots of different, I say lots, there's several different correlation coefficients you can use, and in this class, and the traditional one would be the Pearson's correlation, or Pearson's R. And so the correlation, so in Pearson correlation coefficient, it's defined as the average of the product of x and y. So that's this, when x and y are in standard units. So this equation here is putting them into, what is this right here, which is this, is putting the x into standard units, and that's putting y into standard units. In data science and math in general, you'll typically see things as standardized or normalized. So sometimes people mix these up or use them interchangeably, but they're quite different. Normalized is when you take a data set with some range, which could be anything, and you just set the units so that they're between 0 and 1. Whoops. And so that's not what we're talking about here. Standardization is when we take whatever our data set is and we set the mean to 0 and we set the standard deviation to 1. And the intuition behind that we'll see in the next slide. But that's a completely different operation than what we're doing with normalization. So we set the mean to 0 and then the standard deviation to 1. So this would be like 1 sigma, 2 sigma. Okay, so on and so forth. So this is standardization, not normalization. And the reason why we do this is because it makes things very nice for us when we're trying to calculate the correlation. So we'll go, and just remember, so that none of you forget, this is the symbol for sigma, this little thing like that. And we're taking, when we standardize it, we're taking x sub I, which is the value, minus the x bar or mean, and that's being divided by the standard deviation of x. And it just gives us the, a measurement of the number of standard deviations that are above or below the mean. So we can actually say, of course, whenever we see 1 over n times the sum of n, when I equals 1, this is going to be a signal to us that we're taking an average. And then we have the x sub I here. So this is going to be, for our data sets, x sub I in standard units. And this is the same thing for y, standard units. Yeah. Okay, so what's with the standardization business? Well, I'm glad you asked. This really comes from this idea of the product of x and y. And what we mean by product here is we mean, this operation. Why are we taking the standard units of x and multiplying them by the standard units of y? And then, the sum is just, that's kind of a trivial thing that we'll see. But why are we doing this operation here? So what we really care about is signs. And the reason why we really care about the signs is because once we've taken our data and we've standardized it, remember we've got a mean of 0 and a standard deviations of 1. So let's just assume that we have this data set here. Maybe we'll use, let's use blue, purple, green, something like that would be good. Okay, so let's just say we have a point here, here, and these points really, don't get hung up on the numbers or what the point or anything like that. It's just a little data set that we have. Okay, so here we have this data set, and we want to know why. Obviously, what we've seen from the figures before, right? Like this looks a lot like this. So this is certainly, a very tight-fitting data set. So we're going to say that this is there's a strong association here, and this is a strong positive correlation, right? Nothing wrong about that. So why is that so? Well, if we look at this plot here, we have 4 quadrants, 1, 2, 3, and 4. And we could say that the points that fall into this quadrant, this first one, maybe we'll title these, call this 1, 2, 3, 4, and I forget now if they go counterclockwise or clockwise. I'm pretty sure this is the traditional way of labeling them. Anyways, but the points, use yellow for this. The points in the top right, so in 1, are when x sub I in standard units are positive and y sub I in standard units are positive, right? This makes sense. Let's say for this point right here, this is like, 1, 2, 3, 1, 2. So this would be like 2, 2, 3 for this point, something like that. The point is that a lot of points. The point is that both those units are positive. So in this one section, we have, which would be the, you already know the top right. Get rid of this. We know that we have x sub I in standard units, we're going to have a positive value in y sub I in standard units with a positive value. And this works out nicely. And what can we say about this quadrant? Well, we can say for this quadrant, for this data set, all these points, right? Like all these points fall in quadrant 1. All these points fall in quadrant 3. And there's a couple points in quadrant 4 and a couple points in quadrant 2. And that count, the number of points that fall in each of these quadrants, is extremely important. Let's just make up a number. Let's just say that there are 100 data points here. And we'll just say that, for argument's sake, we'll say that probably about like 40% in quadrant 1 and about 40% in quadrant 2. And we'll say there's about, that'd be 80, so 10 and 10. This looks, let me write this all better. Okay, so we'll say 40% in 1 and 2, and then we'll say there's about 10% in 3, sorry. %40 in 1 and 3, and then 10% in 2 and 4. Okay, so what can we say about the bottom left in this case? Even we've laid it out in plainly right there, but let's make it a little bit more explicit in this quadrant 3 right here. So in quadrant 3, we have x sub i's in standard units, as well as the y sub I in standard units are both negative. And when you have a negative times negative, you get a positive. So what we can say is on average, right? On average, look at these percentages. There are more points that fall in quadrant 1 that are positive, and there's more points that fall in quadrant 3, which wind up being positive. Then there are points in quadrant 4 and quadrant 2, which if you're in quadrant 2 and quadrant 4, you've got at least one negative number. Like this one might be negative 2, 1, and this one right here might be positive 2, negative 1. So in quadrant 4 and quadrant 2, you have negative points. Well, the reason why this is strong positive correlation is because of all the positive values we have. They far outweigh the couple of negative values that we wind up having. And if you were to take this data set here and rotate it down like that, then you'd have more negative numbers than you have positive numbers. And so it's all about the signs. The number of signs you have from these data points on average indicates whether you have positive or negative correlation. And we can see these correlation coefficients visualized. Negative 0.121. Negative 0, first of all, we'll just we'll put this guy right here. And we'll pretend that was always there. 0.02. Negative, okay, well, not off, but not too far off. 0.949. 0.8, not doing too well. Okay, so maybe I need to go back and play more of that game. But regardless, it's quite clear from these plots that this is a strong positive correlation, because we know that the strongest possible positive correlation would be 1. And we know that this is a little bit worse because the diameter of the tube needed to encircle this data is much larger than the diameter of the tube needed to encircle this data. This has, whatever correlation, nothing useful, negative 0.121. Might as well be 0 at this point. Now, with 0.12, there's a small amount of correlation, but it's negligible and not something that, like, let's say in a predictive algorithm, not something that not a pattern that you might be able to make use of. Though, however, as we will see at some point, when you're creating linear regression models that have multiple features in them, you want to use features that are not positively or negatively correlated. Because if there's a feature that's correlated like this, let's say this is two features in our data set, x1 and x2, and we see that they have positive correlation, well, the kind of the statistical structure for one variable is explained by another variable. So by adding both these variables to a machine learning model, we would be kind of adding duplicate information that, that variance of that one variable x1 is kind of encoded in x2 or vice versa. So you probably wouldn't want to use both those variables. You'd want to use just one or mix both of them together somehow. Whereas if we had x1 and x2 here, this does not have correlation. So these two variables don't explain the same variance in your data set, and thus you'd want to be more likely to use them. We call this when you have multiple variables that have a strong type of correlation that are highly correlated. We call that multicollinearity, and regression models tend to not like to have collinearity in them too much. There's always exceptions, but in general, that's just something to watch out for. A little tidbit from this lecture. Okay, and again, this absolutely zero correlation, even less than this, even though this has a much higher association than this. Like this is strong association, but no correlation. This has neither association really nor correlation. Okay, so hopefully that kind of gives some insight into correlation. Now let's go ahead and bring it back to our formulas, because we said before that correlation and the formulas for the slope and the intercept are very tightly kind of belong together. And in fact, they actually do. We can see right here that the correlation can be found within these equations. And we want to kind of explore this. Why is it that the optimal slope for the linear hypothesis can be written in terms of R? Why can we write this in terms of R when trying to find out the optimal slope? And the same thing can be said, there's a concise way of writing, this just becomes that. But this is really the meat that we want to look at. And really in this class and in general, there's a lot of ways to manipulate the formulas for the slope here. And depending on the kind of problem you're trying to solve or what exam question you're trying to solve, perhaps in your case, using formulas like this in different contexts, right, can give you kind of a benefit. And we'll see that actually when we go ahead and prove that this is true, right? We want to prove that this is equal to this. So let's go ahead and do that next. Okay, so prove that W sub 1 star is equal to R times sigma sub y over sigma sub x. So, we want to show that, in order to get the optimal slope, which we've already proven before to be this, actually is also just this. And that correlation equation we got from back here. Okay, so what's the first thing we want to do? Well, first thing we want to do is we want to write this down, because that's what we need to, this is what we've already proven, this is what we have, and this is what we need to work with. So let's go ahead and do that. So we have W sub 1 star equals, and this is this big convoluted thing, x sub I minus x bar times y sub I minus y bar over, over, again, the sum of x sub I minus x bar squared. Okay. So we want to rewrite things in terms of R. So let's go ahead and look at this formula for R. And we can, how do we want to do this? Yeah, let's keep things side by side. Okay, so that would be R is equal to 1 over n times the sum of x sub I minus x bar over sigma sub x over the standard deviation. Same thing for y sub I minus y bar over y. Okay, so what's something that we notice here, right? We're trying to, we have something in terms of R, and we want to manipulate this to get this to behave within terms of R, right? Because at the end of the day, we know W sub 1 star is equal to this, and we really, in order to prove this, we need to get it into this form. So how do we do that? Well, we need to start rewriting things in terms of R. We've got our R right here, and we have this, we have this nice kind of complicated looking thing. And look, we have the same kind of complicated looking thing right here. So if we can just rearrange this equation and we have an R, then we can probably substitute out this entire thing here for how we rewrite this. So what can we do? Well, we know that this is x sub I. That's not a constant. X bar is a constant, but we want to keep that because we have that here. Well, what other constants do we have that we can pull out? We have these sigmas. So these can just, fly away and go on the other side. We can kind of pull those out. So what does that look like when we pull those out? Well, we still have R. Maybe I'll put this into blue. So we want to take this and multiply or remove those. So let's go back to orange. So we have R equals still 1 over, in this case, n, but now we also have these other constants we've brought over. So the 2 sigmas, this is just all multiplication, right? And then we're going to times that sigma now, and that's going to be this x sub I minus x bar times y sub I minus y bar. Now we have this nice looking thing right here, and we're cooking because we have the same thing over here. We just got to deal with this mess real quick, which not really that difficult because we have a 1 on top, so we can just multiply through and take this n and the 2 sigmas and put it over there with the R. So I'll just do that again. We want this and this and this, and that goes there, there, and there. Okay, so let's rewrite this. So now we have R times n times sigma x y, and that equals x sub I minus x bar, y sub I minus y bar. Now we have, and I'll just circle this. Now we have this, which can go, it's horrible. Actually, it's a different color. Let's use, I want to use blue. All right, we'll use red. We have this, and now this goes there. So this is 1, and this is 1. So actually, it's not, let's save those actually, because if not, that will be look a little confusing. So let's go back to this now and rewrite this. So we've got our W sub 1 star, and now that equals, we've replaced our numerator. We haven't replaced the denominator yet, but we will, so let's not write that. But this numerator has been rewritten as R times N times the sigma X, sigma Y. Okay, so let's go ahead and do this next part. And we'll do that in yellow as well. And then now I guess it also makes sense to take, this one goes there, that one goes there, just so you can see where they're being copied over. All right, so let's see. Okay, so we want to use something that's the standard deviation of x. And we can write this equation down. Standard deviation of x is equal to, this will be the square root. Let me just write the interior first, so I can see how large I need to do it. And that's x sub I minus x bar. And that's going to be squared. And we're going to put all that underneath the square root. Okay, so let's see. What do we have? We know that we have, from our original equation over here, we have this colossal thing. And we know that we need to, just like we did before, isolate something in terms of R that looks like this. So, or in terms of standard deviation for X. So we know that we have, and the reason why we want standard deviation of X is because eventually we want to clean up some of this top stuff here. Because we need to get the standard deviation of y alone on the top. So we're going to need to deal with these things, and this R can eventually just pop down once we have something in the denominator. In the denominator, we need to get just a single sigma x, which we have right here. So we can work with this. And we know that this part of the equation here looks a heck of a lot like this. So let's deal with this square root, and let's deal with this 1 over n, and then we'll be well on our way to victory. Okay, so we can do this in 2 steps to make it extremely explicit. So let's just take the, let's just start with the with the square root, because we can just square both sides and get rid of it. So this will be sigma sub x. write that a little better. Squared equals 1 over n, c n I equals 1, x of I minus x bar squared. Okay. Now we just need to deal with the 1 over n, because again, this right here looks a lot like that, exactly like that. So to deal with the 1 over n, that's quite easy. We'll just multiply n onto both sides. So this n we'll want to just bring over there. And that will give us n sigma x squared equals sum of xi minus x bar squared. All right, so we now know that we can rewrite this as this. So let's go ahead and take just to show you. And so now this is 2. We're going to put 2 over here. And we'll just purple, this is going to be n times sigma x squared. Okay, so w sub 1 star equals, there's a couple of things we can do here. 1, these n's will cancel out. We can remove this by taking one of these standard deviations of x can be canceled out with one of these. So maybe I'll just type it in red, or put it in red. So this n goes away, that goes away, and that goes away, leaving us with, and we'll pop the r off. So r times y over the remaining x, and that looks a lot like what we have here. So thus we've shown how we can get from these complicated equations for the slope, or for the optimal slope, through the correlation as well, which makes a lot of sense because the correlation is going to show us that best line that goes through it's kind of the slope of that would be. So we can get there both ways now, through this as well as through this. Why do we care about doing this? Well, one is to show you that they are the same. That's a nice fact to now know. But furthermore, you can now use these equations interchangeably, which you can see how useful that can be when you're trying to solve for different problems. But all right, let's go ahead and move on to the next thing. Okay, so in class, we'll go ahead and look through some code for simple linear regression. I'm not going to do it in this lecture, mostly because I'm recording this on the iPad, and sitting here writing code would not be very easy. So in class, we'll go ahead and work through this, as well as some additional code stuff. But for now, going forward with the rest of these slides, this regression line here is the best regression line for this data set, and that equation is right here, where we have 142.25, which is the intercept, and then 8.19 would be our slope. So this is 142.25 would be our W naught, and this 8.19 would be our W sub 1. And note that 142.25 isn't right here, but we're at 6 and not 0. But if we were to bring this to the 0, then it would be, somewhere over here. So in these next slides, this is our equation that we'll use, because we're going to want to interpret what it is exactly that these mean. Okay, so this is our slope, W sub 1 star, and it's the best slope that we've determined. And this is really what we're interested in right here. Now, important to note that, maybe we'll choose purple's fine. We have these sigma sub y, sigma of x, and then r, which is our r value for the Pearson's r coefficient. And it's important to note that this r has no units. But sigma of y and sigma of x, this is important because this does have units, and the units that both these are in are, very naturally the units of y and the units of x for our data set. So in this case, we're back to our data, minutes to school, and hour departure time. So x here is in the terms of hour, and y is in terms of minutes. So hours, minutes. And what the slope is doing is it's really measuring how much our predicted commute time will change in hours per minute. So, or as I say, units of y per units of x. So in plain parlance, we would say for every hour you leave later, you will get to work 8 minutes and whatever 0.20 of 1 minute, right? 8 minutes and 0.19 of x, which would be minutes. So you get there. So 0.21 minutes of 1 minute is probably about 12 or so seconds. So 8 minutes and 12 seconds faster, since our slope is going down. So for every hour of departure time that we increase, right? So every hour later that we leave, we decrease our commute time by 8 minutes and about 12 seconds, right? So from 6 to 7, that's right here to right here, we're decreasing it by about 12 or 8 minutes and 12 seconds or so. And let's maybe make this just a little bit more explicit too. We have units of x and units of y. And so for x sub I, we have departure time in hours, and y is our commute time in minutes. And again, x departure time in hours, y commute time in minutes. X departure time, this is hour by hour, and y commute time in minutes, minutes to school. So that's how we interpret the slope in as far as actually looking at the units of measurement. And just to write this one down, 8.19 minutes per hour, or 8 minutes and approximately 12 seconds. Decrease every hour later you leave. Okay, so what does this actually look like when we plot this? And this is a typical misconception, and this is also one misconception that I see a lot in Cogs 9 when I teach it, and that's that when people kind of see slope, they think the correlation. So, for example, if they were to have, with a plot, something kind of like that, right? Which is pretty flat. This the slope is low slope. They would say that this is no correlation, right? So like if low slope, then no correlation. And this is simply just this is simply just not true, because slope does not equal correlation. And we can see that here. Let's go ahead and draw a line for all these. And we could do something like, the best fit line would probably be something like that. And this one would probably be something like this. And then this one would probably be something, like that. And we would say that, the slope of all of these is different. So we've adjusted the slopes by kind of keeping either the x or the y constant and then stretching the x or the y. So in this case, this is our original one, and for this one the x stays the same, and then we take the y and we kind of like we stretch it along here. And in this case, we take the y and we keep it the same, and we stretch the x. In this case, by stretching the x and keeping the y the same, we decrease the slope. So for this one, the slope has gone down, and for this one, the slope has gone up. Maybe I'll actually just write that. So in this case, slope goes up. In this case, slope goes down, because we've stretched this, and then we've stretched this one relative to this first plot here. So in this case, the correlation is the same between all of these. So the slope for all three are different, but correlation is the same. So that's an important thing to keep in mind. In the case for these two plots, the slope gets steeper. So the further away from zero it gets in this one, the slope gets more shallow or closer to zero. So the slope gets closer to this point here, and it gets further away from the origin over here. And yeah, that's something to think about. And when we say the correlation is the same, I guess I should also add the, maybe I should actually rewrite this, be a little bit neater. Correlation, in other words, the R is the same. Those have been the same thing, just making it explicit. Okay, so let's go ahead and then we've kind of looked at what the slope means in this case. Now let's kind of think about the intercept. So one interesting thing to note here for the intercept is that, and this is something that we'll think about we talk about this, but just to put this out here real quick, maybe yellow looks best. Let's just assume that this X right here, this mark on the line is the average of both X and Y. So average is the average of X and average of Y. And this is true for not just this particular data set and for this particular best fit line, but this is true for all data sets. We're looking at this linear regression model. And we can show that. That's what we'll do over here. But first, let's think about what are the units of the intercept. So the units of the intercept in this case are in minutes. So the units of Y are in minutes. And this makes perfect sense because this is the y-intercept. And the y-intercept, of course, has to intercept the y-axis, and the y-axis is the amount of minutes to school. So our intercept's always going to be in terms of minutes, and that's what you see right here, this 142.25. This is where this regression line intercepts with the y-axis. Again, this plot, it might be hard to read, but remember this is a 6, and in order to get to 0, it's going to be way out here. It just kind of goes like that. So we want to think about what the value of H star when we plug X bar into it is. And what we can do here is try and show ultimately that when we plug X bar in, or the mean of X for H star, what we get ultimately is Y bar, which is why this here is true. So when we think about this idea of H star, this function H star, which takes an X bar, let's maybe do this in student green, why not? Okay, so we have H star X of I equals W naught star plus W sub 1 star times x sub I. And we want to rewrite this. Now, we know from what the intercept is, which is right here, that we have W naught. Because what we really want to do is we really want to be working in these terms right here, not W naught. So we're going to, maybe we should do this in blue. We want to take this and plug it in right there. So let's go ahead and rewrite this now. This will equal, and maybe we'll keep the blue. This is going to be just y bar minus w star sub 1 x bar. We'll go back to green, plus w sub 1 star times x sub I. Now then, we want to be able to rewrite this, and we have this w sub 1 star x bar plus w sub 1 star xi. We want to kind of combine these, thinking about factorization. So let's go ahead and do that. So this would give us still y bar minus would be w sub 1 star times x bar minus x sub I. Now, this is something that we're pretty familiar with. However, we usually have x sub I, minus or plus x bar. We want to rewrite this with a positive sign. So we have something like x sub I minus x bar, which is what we usually have because we have some value, x sub I, and we're typically taking away or subtracting the mean. So we can do that by manipulating this sign right here. So this will just equal y bar plus w1 sub 1 star times, and then we can flip these around, and it will give us x sub I minus x bar. Now then, we know what x sub I is because in this case we're saying that we're plugging in x bar. So remember, this is, I'll just write that down to make it a little bit easier to read. We have h star, and in this function we're plugging in x sub I. So remember, essentially this x bar. So this x bar is the value that we're plugging in for x sub I. So what do we get when we do that? Maybe I'll just go over a little bit. We have y bar plus w I star, and I should probably okay, plus w sub 1 star times, remember we have xi, but we're plugging in x bar. This is x bar minus x bar, and x bar minus x bar will just give us 0. And what we're left with is W sub 1 star times 0 plus Y bar. So this is going to be equaling Y bar. So we have H star taking an X bar, we get back Y bar. Thus we see this average of X and average of Y here. Now another important thing to note about the intercepts is when we plug in, let's say, let's do this in purple. If we have H sub 0, what does that give us? And remember, we really care to think about what happens when we're at 0 on the x-axis. What's happening over here? So the departure hour is 0. And in this case, for this data set, that's when our departure time is at midnight. So, because remember, we're in the units of our x, which is departure time in hours, and this is a scale. And this, well, let me just write this down real quick. Which equals the commute time at 24 or midnight. Remember that this line goes on forever, right? So we could technically take this line and predict what our commute time would be when we leave 5 days ago or 5 days in the future. The thing, though, is that, of course, those are kind of meaningless predictions, because if we leave, let's even take, for example, this midnight. If we leave at midnight, we're going to say it's going to take 142.25 minutes to get to school, or to get to work. Or no, sorry, to school. That makes no sense, right? Because at midnight, there's no one around. And it should be even quicker to get to school than it would be at, let's say, 7 a.m. or 6 a.m. Right? Like it would almost seem like if this was the plot, and this was 0 midnight, that it should kind of go like that. But it doesn't, because this is a linear model. So this line is not a quadratic, whatever. It's a linear model, not some nonlinear model. The thing, though, is that in our data set, we didn't have any times where we left at midnight. If we did have times we left at midnight, then, and let's say that those in realistic terms might be like, like around here, maybe a little faster, maybe like 50 and 60. Like, let's say those are the times we had when we left at midnight. Then this line would look more like this instead of like that. But since we don't have those times at midnight in our data set, our linear model isn't really learning to deal with the concept of leaving at midnight. Therefore, it doesn't really care about it. It's not representative in our real world data generating process. And remember, this data comes from a real world data generating process. That data generating process is our departure time. And in that data generating process, our departure time is not at midnight. Thus, this model doesn't capture that real world scenario. So this is also another really good example, thinking about this theoretical aspects of a linear regression model, why the data is always, the key player here. It's the most important thing, no matter how good this linear regression model might be. If the data doesn't represent what's happening in the real world, it doesn't matter. Now, that's only if we care about predicting times when we leave at midnight. I don't think we really do. In this case, it doesn't really follow with the story of leaving at midnight, because you don't go to school at midnight, therefore we don't care about it. But it's just an important thing to keep in mind and note. All right. And we're kind of, this lecture is kind of getting to be a little bit long, so we'll kind of blast through the rest of these slides. But really quick, take a pause and see if you can reason through this answer or this question. And this is, a similar kind of question that you'll see on the exam, perhaps. It's a little tidbit, but try and think about this idea. If we fit a regression line to predict commute times given departure hour, something we're very familiar with at this point. If we just add 75 minutes to all the commute times in our data set, what happens to the regression line? Okay, so what we really want to think about here is what the happens to the slope and what happens to the intercept. So sometimes drawing a picture can be helpful. If we have this, and we have our commute time, and we have our departure time, what is going to happen? And we'll have, something kind of like our data set right now. That's just an example. And we have, our line just like this. So then what happens if we take this and we add $75 to each uniformly? Okay, so the answer can't possibly be A or B because the slope doesn't change. It can't increase or decrease. The slope for this, which was like this, will just be like this then. See, they're the same. And the reason why they're the same is we just have to look back at the equation for the slope, which is right here, and we have our correlation coefficient, R, and we have our standard deviation of Y and standard deviation of X, and none of that is changing when we just add 75 minutes, right? Like the standard deviation doesn't change for Y or X, nor does the correlation coefficient, because if this is our line and this is our new line, the data is still spread out uniformly around that line as it was before the value of 75 was added. So we know the slope stays the same. And we also know that the intercept can no longer stay the same because we're adding 75 minutes to our commute time. So departure time is not changing at all. We're only adding it to the commute time. So all these values are moving up 75 units along the y-axis. Therefore, our correct answer here would be C. So, this is a nice kind of thoughtful question to think about. Okay. This correlation mean squared error, I will suggest for all of you to work on trying to prove this yourselves for some extra practice. And I'll probably put up an EdSTEM post on trying to, or showing you the proof for this a little bit later. But I don't want to spend too much time in lecture on this because we have to go forward. But this is a, somewhat important thing to think about. But try and work on this slide on your own, and we'll revisit it with a post. Okay, so one thing that we do want to wrap up though with is talking about how we can compare what we've done so far to other models. And honestly, what it really comes down to is thinking about a model where we have some sort of line, and this line passes through y-intercepts at a different point, versus a model that only passes through the origin, right? And how can these two types of things compare? So this is kind of the last thing we want to talk about in this lecture. And to do that, we'll kind of think about this question. Suppose we choose the model hypothesis function h of x, and we equal that to w sub 1 x and squared loss. So far everything's staying the same, except we're not dealing with an intercept anymore. So right off the bat, and I apologize for this, but of course b and c are the same, so maybe we can just not think about this right now. Oh man. Okay. So we know the answer can't be A because A is the traditional thing we've been working with, and we're no longer trying to minimize for a function that includes an intercept here. So, and remember, we have this w sub 1 x right here, which means that, you know, we have a line going through the origin. So you know, what do we want to think about as the correct answer here? What is the optimal model parameter for w star sub 1? And this is what we'll spend the rest of this, the next part of lecture looking at, but we'll show you that the correct answer will in fact be B. And we'll go ahead and look at how that works and why it's also not D, even though it's pretty, could be convincing, but ultimately it's not going to work for us.